is the best way to go. And by the way, this corresponds to the second step. So starting at x equals 0, we went to 0.1, 0.2, and the calculated y value, 1.22. Now, there's nice patterns that you can use with your calculator. So it's going to be that value for my y, 1.22, plus step size times, and I'm plugging in 2y minus 1, 2y sub 2. So in your calculator, this is the way I do it. So I hit enter already. It's got that 1.22 in there. So add that, just hit plus, step size, times, and I know that that previous, the function f of xy, I'm using my previous y value, right? So it's just 2 times that y value, and check this out, it's second answer. 2 times that previous calculated value minus 1. And we get 1.364. So that is the calculated point 0.3, comma 1.364. Okay, again, y sub 4 is going to be that y value plus step size times 2 times that y value minus 1. And I don't even have to type in anything. Use those calculated values. Oops. 1.5368. Yeah. I think I only have to hit enter after that. So we get 0.4, comma 1.5368. The calculators are smart. They understand iteration. Previous answer is going into those spots, and we get 1.744. So that is my, in other words, that was corresponding to the 5th step. So y of 0.5, and this is an estimate, 1.744. Okay? All right. So what I want to do is compare this. All right, so y of 0.5, approximately 1.744 to the exact value. All right, and we have an exact function right there. So y of 0.5 gives me 1/2 1 plus e to the 2x, and 2 times 0.5 is 1. So 1/2 times 1 plus e. What's that?
That's 1.8591.
8591. Okay. Dot, dot, dot. All right. So, close? Well, yeah, that's subjective. If we kept iterating, right, that error would sort of propagate itself. So how close is close enough? That's subjective. It depends on what you do. Okay. One thing we can do is find what's the percentage error. Well, let's do 1.744 minus the exact value, 1.859, divided by the exact value.
6.19%.
Is that right? You did the difference?
Yeah.
Okay, and divide that by the actual value, so error divided by the exact value gives a percentage off, 6.19%. Negative. Technically, yeah, the negative could just mean if that is an underestimate to the true value or an overestimate, yeah. So under by 6.19%. Okay. So Euler's method can be, well, it's very computational, obviously, yeah. All right. So good thing is though, there's other ways we can do it. Now, things that are good for iteration, computers. There's all sorts of programs you can use. What I'm going to do is show you Excel, and I'm going to have both of these up. I have the template, and I'm going to show you how to build this thing. I'm going to put the template and then the finished Euler's method, both of those Excel files, so you can play with them and adapt them to different equations. Okay. All right. So let's blow this up a little bit, 110. Can we see that? All right. So I got my step size here, and I put it at 0.1. All right. The x value, y values, this is just my initial condition, so I'm literally just going to highlight that. Okay. In blue, that's my initial condition. All right. So dy dx. This is going to be the calculated values, dy dx, and how did we calculate it? What was the original differential equation? So we put that formula in there. It's going to be 2 times, and it only depends on the y value. So at this point, 0, 1, it's 2 times y, just click on it, minus 1, enter. So dy dx at that instant is 1. We go off in that direction 1 unit. Or 0.1, sorry, 0.1. Okay. Now, what I need to do is build in a little mechanism that's going to update this, because my next x value needs to be 0 plus, so my starting x value plus my step size. So I can go, well, equals, put in a formula, click on the starting x value plus delta x plus h. Hit enter. There's my 0.1. Now the problem is, if you drag this to fill it down, it doesn't update that, it doesn't refer to the same step size. It's referring to 0 over here. So if you look at these formulas, C4 plus A4, it's not keeping that same cell and adding it to the previous.
So wait, can't you just drag down the other side?
You could drag down the other cell, but there's a way to do this. And I'm going to put, don't worry, this is going to be in the final product. Dollar signs. Put dollar signs in between, hit enter. Now watch this, when I drag that click and fill. There we go. Okay. All right, now, to get my next y value, this is where we build in Euler's method. Okay. So my next y value, based on the first, is going to be previous y value plus step size h times dy dx. That's the slope at that point. Now, I'm going to put the dollar signs in there because that's going to keep it referring to the same cell that's at 0.1. All right, good. And dy dx, I could just drag this down, and we got one nice cell's worth of stuff here. Now, highlight that whole row. 0.2, 0.3, 0.4, 0.5, boom. And look at that row. That's fine. Okay. And there we go, 1.744. Okay. Now, if I wanted to, I could click this as far as I want. That's the beauty of Excel, is I can go as far as I want, and there's my calculated value. Previous y value plus step size times E12, which refers to the slope of this previous point. Okay.
How much more accurate
Oh, and yeah, when you put those dollar signs in there, I can change my delta x. Say I change it to 0.01, hit enter, it updates everything, but I gotta do a lot more iterations to get to 0.5, don't I? And I just do the pull it down as for a while technique. I don't wanna calculate ahead of time what cell I need to get to. There's 0.50, we get 1.84579. Okay? All right. But other cool stuff, and I'm just going to go, I'm going to change this back to point, what was it? 0.1. Okay. All right. The other cool thing I can do is I can grab all those, all the X column and the Y column, and insert scatter plot. This is going to do a scatter plot of points. So there's my curve, the approximation, and notice we approximated the point starting at 0, 1, known, and these are approximations all the way up to 0.5. So that gives me the overall shape of the curve right there, yeah?
Well, shape of the approximation.
Approximation curve. All right, well, I picked an example that we could do exact, right? So here's the exact. And what was the formula for the function we got? 0.5, and let's factor that out, times. You need to put those times, when in doubt, put times in between things you need to multiply. And then it was 1 plus e, and just use exp to the, what, 2x? 2 times, and the x column, notice y is a function of x alone. I don't need to put y in there. It's just click on that, 2x, parentheses, parentheses, boom. That's the exact value, which we know is 0, 1, and drag it down to 0.5. There's my 1.85914. Okay? So in the case when we can do the exact, I can put a parallel column down there and compare the values. Right? Now, let me carry this down to 1 and show you what something we can do. I can highlight that. Let's insert this scatter plot again. Right click, select data, edit. I'm going to call this approximate solutions. Okay, there's the approximate curve. Now, what else could I do? I'm gonna do the exact function with it. Go back to select data. I can add series name. I'm gonna put exacts. X values are coming from the same inputs, and Y values coming from this column. There we go. Okay, so you can see them, and then you can put some in there. You can name them whatever you want. So the approximate looks like it's underneath. The other thing, the exact curve is concave up. So at each point, the tangent line is underneath it. We go a small distance, calculate our approximate point. Change our direction, go a small distance, calculate our approximate point. Okay?
And concave down is always going to be like an overestimate, right? Concave up is always going to be an
Right,
overestimate.
right. If you get something that's more complicated, it can change, and yeah, your Euler's method is always kind of lagging behind a little bit, those changes in concavity. Anyway, so I think it would be a good idea, why not just look at number 3 in class? This is just an activity.